Hello everyone, my name is Dara Franklin and I'm a mechanical engineering major and I'm the team lead.
My name is Alexi Seguero. I am aerospace engineer and I'm the chief aero engineer for this project.
My name's Anatuba. I am an aerospace engineer and I'm the testing and quality control lead.
I'm Cole Cartier. I'm an aerospace engineer and I'm the procurement lead.
My name is Wyatt Doherty. I'm an electrical and computer engineering major and I'm the electrical lead.
My name is Conray. I'm an ECE major and a DSP lead for the ERSD project.
And we are team 26036, sponsored by General Dynamics, and this is our emergency signal relay drum.
After natural disasters, it is common for coastal communication towers to become damaged or destroyed. This leaves first responders, such as the United States Coast Guard, without reliable communication coverage. Our project, the Emergency Signal Relay Drone, will serve as a temporary replacement for these disabled towers until permanent infrastructure can be repaired. And so the goal for our project is to design, build, and demonstrate an autonomous drone that deploys without a runway, has over 1 hour of flight time, and is equipped with a payload capable of supporting disaster recovery operations. The system will receive and transmit U.S. Coast Guard emergency transmissions while loitering around a designated waypoint. Our design prioritizes ease of use, transportability, and safety.
And in order to satisfy this design, we decided to divide our project into 5 subsystems: airframe, communications, GNC, power, and launch.
The airframe for this project is the Recon, a fixed-wing drone designed by Titan Dynamics. The structural design, high aspect ratio wings, and spacious fuselage made this option compatible with our requirements. Since the aircraft is required to operate in 20-mile-per-hour winds, we estimated the aerodynamic stability derivatives of the Recon using XFlyer 5 and performed both static and dynamic stability analyses to ensure that the aircraft will remain stable in these flight conditions.
Structural requirements specify that the airframe must withstand aerodynamic and launch-induced loads with a minimum factor of safety of 1.2. To address this, preliminary finite element analysis was conducted to evaluate stress distribution and identify critical load paths within the wings and fuselage. These results informed reinforcements in high-stress regions. The airframe was manufactured using lightweight PLA to achieve a high strength-to-weight ratio while maintaining performance in humid coastal environments. Internal structure was optimized through selection of infill percentage and infill geometry to maintain proper strength and durability while minimizing mass. The airframe was made through additive manufacturing, allowing for in-house production as well as ensuring ease of repair. Due to the absence of existing print profiles for lightweight PLA, a custom configuration file was developed and refined through iterative test prints. Initial prints exhibited issues such as under-extrusion, core layer adhesion, and extreme stringing of filament. This guided adjustments to parameters including temperature, flow rate, and print speed. These adjustments resulted in consistent, high-quality components such as this one right here. Structural validation was performed through wing loading tests, where distributed loads were applied to simulate aerodynamic forces. Measuring performance was consistent with FEA predictions, confirming that the airframe meets the required factor of safety under expected operating conditions.
The communication system on the emergency signal relay drone is designed to act as a long-range relay between ground users and distant infrastructure. In a disaster scenario where traditional communication towers are down, the drone essentially becomes an airborne relay station. This is made possible using a full duplex software-defined radio made by Libre SDR, controlled by an onboard Raspberry Pi computer. Signal processing is handled in real time using a new radio flow graph, which allows us to filter, process, and route signals entirely in software. One key advantage of this approach is flexibility. The transmission channel can be adjusted directly in the new radio software within the Coast Guard frequency band from 410 to 420 MHz, ensuring compatibility with onboard filters while still allowing adaptation to mission needs. After processing, the signal passes through bandpass filters and an amplifier to maintain signal quality and extend range. Frequency-matched antennas mounted on the wingtips help reduce interference and maximize overall communication performance. We perform signal interference modeling to determine the proper separation distance of these antennas. In operation, the system can receive signals from up to 20 miles away and retransmit them up to 50 miles, as seen by our radio coverage simulations on Radio Mobile, with the output signal being transmitted with about 1 watt of power. We verified these results by performing spectrum analysis and secured solid margins on our signal links. We also eliminated any signal spurs, harmonics, or noise. Take a listen to this audio test from Conray.
Next, I will transmit a voice message at 156.8 megahertz, and hopefully you will hear a crystal clear sound at 420 megahertz.
This is the testing signal of Team 26036 Emergency Signal Relay Drone. Testing 1, 2, 3. Testing 1, 2, 3.
The GNC subsystem handles the flight planning requirements of the system, where the drone must be able to accept GPS coordinates and sustain a loiter. This operates by having a ground control station communicate directly to the flight controller of the plane. Our ground control station is an open source application called Mission Planner. Mission Planner provides a user-friendly UI that provides the health status of the plane, flying visuals, and settings to tune and configure the electronics. In order to ensure our system is user-friendly and rapidly deployable, we wrote a flight script and pipeline that communicates directly with Mission Planner and sends commands to the drone using a communication protocol called Mavlink, providing real-time telemetry data from the drone. These commands are high-level and come from an open-source software called ArduPilot, responsible for the navigation and control to the drone. These high-level commands were entered in the Python script and coded to activate via key presses and inserting latitude, longitude, and altitude. These commands are arming, takeoff, loitering, and return to launch. The drone has an automatic takeoff where the motors actuate the throttle when it registers a specific acceleration, then begins navigating to the designated loiter point. The drone will then transition to fly-by-wire A mode, where an experienced drone pilot lands the drone on the skid plate of the aircraft. The pilot also has control of the plane via the transmitter, where they can arm and disarm, change flight modes, or activate the kill switch to completely shut off the plane.
For our power subsystem, one of our functional requirements is that the system must be capable of operating for over 1 hour flight time. Based on a power analysis using the aerodynamic data of the plane, as well as assuming steady level flight, we determined that approximately 180 watt-hours are required for 1 hour flight, with 25 of those being budgeted towards our communication system. To meet these requirements, we selected a 6S4P battery, which is 432 watt-hours, which provides a healthy margin for our flight time requirement. This battery provides a nominal voltage of 22.2 volts to a power distribution board, which in turn supplies power to the propulsion system, avionics, communications hardware, and onboard sensors. This makes the power system a critical component of overall system functionality, while also being designed for easy accessibility to enable quick turnaround times between missions.
The launch system was designed to enable safe, reliable, and repeatable deployment without requiring runway infrastructure, all while remaining low cost, easy to operate, and with no external power requirements. A bungee-based system was selected to provide consistent and reliable energy input, with adjustable hook points allowing for tuning of launch force based on aircraft mass and mission conditions. The structure supports rapid assembly and deployment by a small team with minimal training. The attachment interface was designed to be interchangeable for reuse with different aircraft configurations.
Each subsystem was developed to meet specific system requirements while also integrating seamlessly into the overall system. Through our design process, we ensured that the vehicle meets key performance goals, including stable flight, reliable communication using the onboard relay, and over 1 hour of operational flight time supported by our power system. We would like to give a special thank you to our sponsor, Jason Landell with General Dynamics, and our capstone mentor, Kerry Jones. We hope to see you all at Design Day.